All right, so welcome to the second session of today. We have Vincent Wang, who's going to talk about constructor theory as a process theory. Please take it away.
Thanks, Paulo. This is joint work with Stefano and Hamza and Carlo and Bob. Maybe an alternative title is a case study in applying category theory. So some disclaimers. I'm the only non-physicist out of all my co-authors here, and perhaps that's for the best for presenting for this particular audience, right? Because constructive theory is, some people say, physics, so I don't know a lot about physics, and also I don't know how to feel about all of this, and you'll understand what I mean. I want some help. I want some help to understand what my emotional reaction should be to this entire project, and hopefully you'll understand what I mean by that by the end of this. And so yeah, just help me out. Okay, so let's get started. What is constructor theory? And if you were to look online, which is a reasonable thing to do, I'm sorry. So you get I think it's ironic because I've actually had COVID for a week, and somehow this is the most breathless thing in my entire presentation. These descriptions of constructor theory as a master theory, it's a theory of physics that makes all these other theories like thermodynamics and relativity and quantum all subsidiary theories. And very recently Marletto has published this book, The Science of Can and Can't, and saying, oh, it's this new way to do all of physics all over, which is of course very hypey, and there are good reasons for that, to make things hypey in the public domain. So the real way to get at what's going on in the science is maybe to ask some PhD students, and that's what we did. So Anisette Vidal and Maria Valiaris, who are two PhD students at Oxford, until recently, they both, I think, submitted just recently, working on constructor theory, were nice enough to come to the Wolfson Foundation's discussions at Oxford, and give us the lowdown on what constructor theory actually is. And so I'm reporting what their description was, and they said, well, look, what is constructor theory as an approach to physics? Well, let's take, for example, the space of all possible tasks, and we'll get to what tasks mean in a second. Well, we can think of tasks as processes, and there are all sorts of processes that happen in nature, like ice cream melts, which happens all the time. It's very unlikely that ice cream is going to spontaneously reform after it's melted. And because of no cloning, it's just outright out of the question that you've got something that can just clone anything, including like turning one ice cream into two. And what constructor theory wants to do is it kind of wants to get rid of this distinction between the probabilistic and the happens all the time and the happens very likely. Just one cut is all that constructor theory wants, just a cut along the space of all possible, or all, sorry, conceivable processes, and to say that everything on one side is going to be called possible and everything on the other side is going to be called impossible. That's it, just a single cut, and ignore all of the nuances of probability and whatever else. Just tell me about the possible and the impossible. And what they want to do is they want to take all of these different domains of conceivable processes that are described by languages, such as the language of processes attracting each other with gravity or thermodynamics or whatever you have. You have all of these different domains of observations, and they say, well, every theory of physics should correspond to just a cut of what is possible and impossible in each of those domains. And you give a cut, and that's going to give you a theory of physics, and conversely, every theory of physics is going to give you a cut. Or this is what they want. This is ideally what constructor theory aims to be. The sort of way of going about physics by just making a single cut along the space of all conceivable tasks. And okay, this was a pretty good description, and of course, it comes time to go, okay, well, now tell us more mathematically about what constructor theory is, right? And if you get over the initial misgivings of, okay, well, a task is a set of this and that, and you go, okay, well, let's not talk about sets. Tell us in English what you really want, then we'll decide together what the nice mathematics is, because that's the nature of this sort of collaboration. Well, you push them at it, and they'll say, okay, well, no, look, it's a meta theory, it's a framework, if you like. Really, what you've got to do is you've got to bring your own math to constructive theory, and you've got to use your own mathematics to interpret all of the English terms that we spell out. So charitably, it's a framework. Uncharitably, oh, it's just vibes, but you have to bring your own math. But okay, fine. So then we ask, what is a task? And they say, okay, well, a task is you get over the set talk, and they say that's a transformation between systems. Okay, and you say, okay, what do you mean by conceivable? And they say, well, okay, a task that's composed of other conceivable tasks is going to be a conceivable task. All right. And what do you mean by a possible task? And they'll say, well, that's just a task that has a constructor. So at this point, we can step back and already say, okay, maybe constructor theory is a bit poorly named. Maybe they wanted to call it possibility theory. And they'll say as much as well, these practitioners, but as everyone knows, constructor sounds a lot cooler than possibility. So constructor theory it is, but really they want to talk about possible and impossible. Okay, and now finally we go, what is a constructor? And okay, at this point, well, we're allowed to bring our own math. So what we did was we started simple. We said, well, we know what process theories are. I mean, we now know of many more sophisticated and nuanced ways of composing processes in space-time, and there'll be some talks later on today that'll go through those. But let's start simple. Just the symmetric monoidal category. We'll talk about tasks as if they're processes, and well, that settles conceivability. We can talk about a process in a process theory, and the process theory gives us the compositionality of conceivable tasks. And then it comes to now we have the sort of mathematical language to start talking about what a constructor is. And now it's on me to tell you what a constructor is. And it's really not that bad. So you've got the what's the systems here. I've got little shoes and maybe some paintbrushes and some paint. And I just want to paint the shoe and call that a task. I want to turn whatever shoe it is, and I just want to cover it with paint. That's going to be a task. And now some jargon will say that, well, there's a sort of shoe wire, and that we'll call that a substrate, because the task wants to act on a substrate and wants to turn certain things on this substrate into other things on this substrate, and everything else just gets bundled up and turned into the environment. So the environment in this case encompasses both the paint and the paintbrush, and how much paint is on the paintbrush, and everything that's not the shoe that we care about. And already we can start sort of getting places with some process theoretic equations. We can say, well, okay, we know what we want to happen after we paint a shoe is, well, we put in any old shoe and it comes out, well, in this case, blue, because that's the color of our paint. But we might use up some paint in the process. And at this point, the constructor theorists will say, no, hold on. What do you mean by the wires and the states? And there's an unfortunate clash of terminology, but because constructor theorists want to talk about thermodynamics eventually, when they say state or microstate, they mean this wire encompasses for them all the potential molecular configurations that could be recognized as a shoe. And out of this space of configurations, this sort of subspace that's picked out by what us category theorists would call a state on this wire is an attribute. They say, well, okay, out of all this space of possible molecular configurations of a shoe, some of them are blue. Some of them turn out to be these, blue colored shoes. And that's this state or macro state picks out an attribute. So this is, we'll call them microstates and macrostates, but we can also call this like the state attribute distinction. Unfortunate clash of terminology, but the idea is clear. This is really just picking out a subspace of just those blue shoes. All right, and okay, so we start with the attributes on the shoe wire that says, well, your shoe can be any color, that sort of trivial attribute. And after the paint shoe, if you put in the environment, a sort of full bucket of paint, you might run out of paint, but you get a blue shoe out at the end. And what that means is that, well, you can start doing a bit of composition as you would in a process theory. You can start with a full can of paint, and you have one shoe here, and you might paint it. And now you're out of paint, but you've managed to paint one shoe. Get that shoe out. Now it comes time to paint the next shoe, and you're out of paint. It's too bad. And this is the point at which we say, well, wouldn't it be nice if we had, a sort of mathematically perfect bucket of paint that just never ran out. So we can paint the shoe again and again. We can paint a shoe again and again blue forever. Sort of like a catalyst in a biological reaction network. And if we did, not saying that there necessarily has to be such a thing, but if we did, then we call that a constructor. This sort of mathematically perfect bucket of paint. Call this a constructor for the task of painting shoes. And somewhat strangely, a task is possible precisely when it has a constructor. So actually, the way that I've just told the story, and maybe a bit counterintuitively, painting shoes in the real world is not a possible task. It's only possible if you can sort of do it to mathematical perfection again and again with the, and have this environment sort of reset itself again and again. So you can do it over and over. And why is that counterintuitive? Well, we can leave that for the questions at the end, but I guess the gloss intuition is that comes down to that way that you want to cut the space of processes into just possible and impossible. So remember that, even super unlikely processes like the ice cream reforming, that just has to fall purely and impossible. And this is sort of the price that you pay is you get this weirdness. But okay, fine, this is a constructor. And then, we can start doing a bit more interpretation and say, well, what does it mean then for a task to be possible? Well, we can say that we can sort of pre and post condition on the substrate and say like, well, we can induce these tasks, and we can sort of talk about the task of turning shoes of every color into blue shoes, and that's something that we can encode in a process. And once we pre and post condition, we have this type checking condition that says that, well, after you use a constructor to perform a task, you get that constructor back and it's ready to go again, right? And okay, this is another wrinkle, another technicality. Because of the state attribute distinction, instead of strict equality, constructor theorists might say, okay, yes, but hold on, the constructor might have all these microstates as well, and you might use it in one microstate of the constructor, but it goes to a different microstate that also happens to be an able constructor for the task. And you go, okay, never mind all that. We'll just give you an enrichment structure so that you can deal with the state attribute distinction, and instead just say that after you use the constructor once, you get something back that's able to be used as a constructor again for the same task. And the constructor theorists say, okay, we're happy with that. And now, well, what can we do? Well, there's some good news. The good news is we get out this idea very nicely that somehow you can just cut the space of all conceivable processes into possible and impossible. In this case, our cuts correspond to taking a sub-process theory or subsymmetric subcategory that's a symmetric monoidal category. And we've got sequential and parallel composition of tasks, which are defined like so. And this is pretty good because, so far all this math feels kind of right. And we're able, and we show in the paper that the possible tasks form a sub-symmetric monoidal category. So indeed, you do have this mathematically clear notion of what it means to cut out just the possible tasks from all the conceivable tasks. And there's some good and bad mixed together. So for example, one thing that you might notice if you look carefully at the definition of sequential composition is that, well, what about the case where you have the sort of same wire and you want to just reuse the same environment to perform the same task twice in a row on, like, say, two different shoes? Well, then you can't compose those wires in parallel. You have to compose them sequentially. And it turns out that this leads to a mathematical difficulty, but that mathematical difficulty, it turns out, is also reflected as a linguistic difficulty in how constructor theorists do constructor theory, because there is a sort of disagreement or let's say ambiguity as to whether constructors are implicitly referred to as the constructor for a task or a constructor for a task. And the constructor reading means that, okay, you're really reusing the same environment to perform a task that, you know, sort of sends attributes to attributes in the same way, whereas a constructor says, no, no, just bring in a new environment every time. So what's kind of nice about this, at least, is that there's some new maths to be elaborated, which is, okay, well, we have to maybe think about what it means to have a partial monoidal category where we demand unique identities on constructors. And also, this new maths corresponds to, you know, clearing up a kind of linguistic confusion in the way that people practice constructor theory. And, you know, there's what we're able to do is turn ugly stuff into good. So this entire talk about attributes and states, which has led to a lot of, which is, you know, taken up a lot of time and maybe been a bit confusing. We say, well, look, it doesn't matter. You know, while constructor theorists want to talk about the, you know, the set of all molecular configurations of shoes and the subspaces that are orange and possibly green or whatever, and the task sends them to blue shoes, we say, look, that doesn't matter because you can just take the set of colors of shoes that you want. And so long as those attributes don't strictly subsume one another, in other words, that your attributes are really distinguishable from one another as sort of informational variables, as constructor theorists might want to call them, then it doesn't matter. You don't need to you know, keep track of your microstates and your attributes separately. Just work directly with your attributes. You know, that's not going to lose you any expressive power. So what we found also is this, you know, functorial coarse graining of tasks that's sort of faithful, and it's you know, preserves everything that you care about, so that you do get this nice abstraction that dissolves unnecessary distinctions. And then there's, you know, just what is the bad and the ugly, which is the principle of locality. I'll hurry through this. This is a dogma that constructor theorists have. Now, I showed this to Anisette, and Anisette said, oh, I love all the rest, but there's just one bit that I can't, you know, that doesn't work out, which is, you know, the principle of locality is a non-negotiable. And what does the principle of locality mean? Well, the B here, no action at a distance, is a physical phenomenon, is a physical criterion, but A is the important bit, saying that the states of a composite is at most the states of the parts. What that means mathematically is that, well, if you have a tensor product, it had better be that the states on the tensor product of two wires had better like inject into the Cartesian product of states on either wire, which is to say that you want your tensor product to somehow have less information at it, or at most as much information as a Cartesian product. So in other words, even using rel is somehow too expressive. So to summarize, the math really does seem to work. So we've got a formal setting for constructor theory that lets us talk about doing these cuts between possible and impossible, and it sorts out some linguistic confusions we have about A and B process. And the math really does work as a good abstraction, because it's really giving us some simplification. And that's the good news. And as far as we can tell, the correct abstraction, or a good abstraction, is just pick some symmetric monoidal category and equip it with a partial order on Hom sets. And that's all you really need to get started playing the game of constructor theory in a formal way. And now, you know, the bad and ugly at once is this principle of locality that constructor theorists want as a sort of physical condition, sort of says, no, well, look, you know, that's all nice, but you can't use anything that's more expressive than rel. You can't use any tensor product that's more expressive than a Cartesian product. Right. And now, well, what is it that we're to do? Well, maybe we can bargain. We can say, well, look, you know, Cartesian product is just one way of mathematically interpreting the language of locality. So maybe there's a synthetic way to talk about locality. Say, never mind. You know, you keep your principle of locality. We can have our own constructor theory with tensor products that are actually sensible and actually work with quantum in a compositional way. Or well, maybe we take them seriously and say we need some new math. We can maybe come up with a way to make everyone happy. Or we can just stop it here and say, well, look, this is not an agreement that's going to be worked out between us. So let's just part ways. And well, we could also, really get down into it and start arguing with them about the physics of it all and say that, well, no, look, the principal locality is nonsense and everything, and this is what you really want because we trust in the math and the niceness of the abstraction. And that's it. That's my talk. And I hope that's painted a picture of a nice little collaboration. So yeah, please let me know what you think and what I should feel about this whole thing. So thanks a lot.
Okay, thank you. Thank you for a talk.
Yep.
And we have quite some time for questions. So let's start with the ones in person. Yes, please. Let me give you the mic.
Hello. Yeah, thank you for the talk. I'm thinking about your example with the shoes and just using the attributes, and I'm wondering, would you consider this to be a linear theory of, I guess, interpreting constructionism?
Could you elaborate on what you mean by linear? I have vibes
Certainly.
about what you mean, but yeah.
Certainly. So a common shortcut that physicists like to make is to take nonlinear systems and linearize them, and you want to form a basis in the vector space. You want to make sure that your x, y, and z, there's no x and your y, and it seems like your red, your green, and your blue shoes are an x and a y and a z distinctly.
Right.
Which to me, if you're saying that the constructivist approach is to do all this stuff, it seems to me that they're trying to avoid prematurely linearizing what could be nonlinear. I just want to see your interpretation of that.
Right. So by my understanding, there are just two dogmas of constructor theory. One is the principle of locality, and the other is something to do with information variables. And the nature of information variables is one really should think of them as essentially sets. And the sort of condition that makes coarse graining work in our setting is this anti-chain condition on attributes that makes sure that no attribute is like contained in another, which kind of speaks to the linearity constraint that you're talking about, I think. And so what that means is maybe they want to avoid prematurely linearizing, but it seems that at the end of the day, what constructor theorists really want to do anyway is work with sets. Like plain sets. Yeah, I don't know if that's answered your question.
Okay, thank you. Any more questions? Yeah, Tomasz?
You? Okay. Yep. Can you hear me?
Yeah, hi.
So the proponents of constructor theory have been arguing for some time that somehow doing constructor theory is something quite different than doing resource theories. So from your mathematical framework or kind of expression of these ideas in constructor theory, does that kind of show up? Or do you think that like the ideas, concepts in this mathematical expression of constructor theory can be somehow mapped and also expressed somehow resource theoretically when you think of partition process theories and achievability orders and so on?
Well, thanks for the question. Well, for some context, yeah, it's on the FAQ site of the constructor theory website. The third out of 3 points is why constructor theory is not resource theory. So they've done very well to try to distinguish what they're doing from resource theory. So what we're doing here is as far as possible, what we did was we interpreted their wishes in the papers that they wrote And in the presentations that we had from practitioners, we interpreted their wishes into mathematics with as few choices as possible, just as close to what they want as possible. So no resource theory shows up in our presentation, although all the ingredients are there. And also, I mean, but by the time you get to category theory, as you're well aware, you're basically able to express one thing in another. And the stuff that you're saying about the reachability of certain processes as opposed to this sort of binary cut, these are all possibilities. But this is not something that was our focus in writing this paper. Really, we just wanted to sort of get the bridge there. But thanks for the question. I hope that's clear enough.
Thank you. Does that answer your question? Any more questions? Okay, not in person. Are there any online questions? Okay, it doesn't seem there are any further online questions, so let's thank our speaker again.